Welcome to our video series on logistic regression. This is our video on multiple logistic regression. Fear not, it is actually very similar to simple logistic regression. So first off, we're going to start by loading some packages. You'll load dplyr, rocker, ggplot2, and caret. And we're going to be using the same video set as their data set as in the previous video. And that is going to be the heart data set. So we already know the num and trace BPS variables, but if you don't remember, num is their risk of heart disease and it's a 0 or a 1, and trace BPS is just blood pressure. We'll also add some new variables to see if we can make a more accurate model. We'll only be working with continuous variables. So this time we're going to look at age and we're going to look at thalach, which is the maximum heart rate achieved by someone. So let's just get these loaded in here. And before making our model, we need to make sure that our variables are not going to be too correlated. And by that, I just mean more than 0.8 is probably too much. Then if you make your model with those all together, they're just going to be explaining each other. So first off, you're just going to take the data set and then remove num, and then we're going to make a correlation matrix and check it out. So it looks like our variables are not very correlated. Thalach and age are a little bit, but nothing is greater than 0.8. So we can go ahead and try to make a model with all of these variables in it and see how that goes. So very similar to making the previous model, we're going to set the seed to be equal to 1 so that our training data set will be the same every time. And then we're going to make a GLM once again. And this time, instead of just having trace BPS, we're also adding thalach and age. And I'm going to also add an interaction between trace BPS and thalach just to see, because we can still do that in the GLM just like a linear model. So once again, you make families binomial, and we put the training data set in there. So let's go ahead and make it and take a look at our model. So these are some very insignificant p-values. I am going to be dropping the interaction, and we're also going to drop age. I know it has a lower p-value than the others. I just know that it's going to work out better in the future. So let's go down here and make another model, this time with just trace BPS and thalach. So let's go ahead and make this model and take a look at it. So we're getting trace BPS having a 0.018 beta and thalach is negative 0.04. They both are significant with p-values less than 0.05, but it looks like thalach is actually even more significant than trace BPS. So this is still a very similar output to a linear model. Now we'll go ahead and try to interpret the betas. So to interpret the beta for trace BPS, we exponentiate it once again. We do e to the 0.018 is equal to 1.08. It's the increase in the odds of being at risk of heart disease as blood pressure increases by 1 and resting heart rate stays constant. If you convert that to probability, we have that for each 1 unit increase in blood pressure while resting heart rate stays constant, you have a 0.018 increase in probability of being at risk of heart disease. If we were to talk about both betas together, you just add them together. So e to the 0.018 plus negative 0.041, which is equal to 0.977. This is the decrease in the odds of being at risk of heart disease as blood pressure increases by 1 and resting heart rate increases by 1. After converting to probability, we have that for each 1 unit increase in both blood pressure and resting heart rate, you have a 0.023 decrease in probability of being at risk of heart disease. So it looks like having a higher resting heart rate is good, and it lowers your chance of having heart disease. So now that we have the model that we want, you can do some diagnostics on it, and that is covered in the next video. Or we can go ahead and decide the cutoff point and everything, just like in the previous video. So we are going to make predictions for the part of the data set that we did not use to make it once again, to see if we're more accurate this time. So this time we predict, and then we put our model, and then we do heart minus the training data set. And then we take a look at it. So this output looks very similar to the previous one. It doesn't look like we have any closer to 0, at least in this first couple, but it looks like we have one that's 0.88 now. So we have gone and gotten higher predictions, which might mean a more accurate model, and we'll see in just a minute. So remember, to find the cutoff point, we are going to make a graph of the sensitivity and the specificity by using the performance function right here. And we're going to decide our cutoff point based on just the graph this time. I'm not going to find the exact value. Looks like it's slightly past 0.4. I'm going to go with 0.42 as my cutoff point. So now we put our predictions and the truth into one data frame. Once again, I'm going to change the zeros and ones into no risk and risk just to make interpretations easier. And then we make a plot of our predictions and see how well we're going to be doing with our cutoff line. So this model actually looks more accurate. We have no risk, they're closer to 0, and by that I just mean they're below the line, which is what we want. And for risk, we have a lot of them are above the line, with seemingly less of them below the line. So this model looks like it might be more accurate, and we are going to get the actual numbers now just to see the sensitivity and the specificity. So remember, we do this by taking the cutoff point and making our predictions 0 or 1 based on whether they are less than the cutoff point or greater than the cutoff point. Then we change these zeros and ones into no risk and risk just to make it easier to read. And then we make a confusion matrix with the positive being risk. So it looks like our model is actually more accurate. I think the previous one had a 0.58 accuracy, and this one has a 0.72 accuracy. The sensitivity and the specificity are very close, which is what we want. They're both more than 70%. So this looks like a very accurate model. Now, remember, the cutoff point does not maximize accuracy. The cutoff point just makes sensitivity and the specificity balanced, so you're not biased towards a positive or a negative. So this turned out to be a much better model with just one variable. I hope that yours turns out the same.